So that was Gibbs sampling. What we're going to talk about next is the Metropolis Hastings algorithm, which is in some sense a generalization of the Gibbs sampling algorithm. I'll talk in a minute about the relationship between the two. So Metropolis Hastings, by the way, is the algorithm that most people mean when they talk about Markov chain Monte Carlo, or MCMC. So this is an algorithm that's quite similar to Gibbs sampling in the sense that we're going to keep generating samples where each sample we generate depends on the previous one. It's also similar to rejection sampling in that we're going to have a proposal distribution, Q of x prime. So this is going to be a distribution that's going to give us the x we're going to sample next. But note that the difference here is that our proposals now, instead of just being each one completely independent, each proposal is going to depend on the x from the last iteration. Also note that when we have x here, we're referring to the full vector of all of our random variables. And this algorithm is similar to rejection sampling in that at each iteration, we're going to propose a new sample according to our proposal distribution, and with some probability, we're going to reject it, and with some probability, we're going to accept it. In the case of MCMC, in the case where we reject our proposed sample, we're going to stay at our previous value of x for one more iteration. That is, we're going to record another sample from that previous value of x. So what we're going to do for the Metropolis Hastings algorithm, I'm talking a little bit about the different possible proposal distributions, but let's define our rejection probability. So our rejection probability is going to be the following. First, for simplicity, let's say our proposal is symmetric. What we mean by symmetric is that Q of x1 given x2 equals Q of x2 given x1. So that is, for any pair of x's, it's equally probable that we'd propose to go from x1 to x2 as it is that we propose to go from x2 to x1. In that case, we're going to use the following rejection probability, and we'll give some justification in a minute for why this is a good rejection probability to use. We're going to use rejection probability equal to P of x prime over P of x. By the way, we're using a star here to indicate that this is the true value of P that we're trying to sample from. So notice that if, and then we're going to figure out this ratio, and then this has to be a probability. So if the probability of x prime is higher than probability of x, this is a value greater than 1. So we're going to take the min of this and 1 to bring it down to 1. By the way, I said a second ago that R was the rejection probability. It's actually the accept probability. I don't know why they used R for accept, but that's okay. Now, if the probability of x prime is less than the probability of x, then this is going to be some value that's less than 1, between 0 and 1, and we're going to accept that proposal with the probability according to that. So if we propose something that's higher probability, we always accept. If it's something that's lower probability, we still sometimes accept with some probability. So one way to think about this, what MCMC is doing, is you can think of it kind of like gradient descent, where we're continuing to move around the space and we're in general going to go towards the high probability regions, but MCMC is going to sometimes go downhill essentially and accept moves that take us to lower probability regions. And of course that's what we want, because we want to sample from the full distribution. We don't just want to find the position with the highest probability. Okay, I said that this is the acceptance probability for symmetric proposal distributions. What about for asymmetric proposal distributions? We're going to do exactly the same thing. We're going to calculate our accept probability as the minimum of 1 and some value alpha. That value is going to be the following. It's this first factor, p star of x prime over p star of x. That's exactly what we had before. We're just adding in this additional factor, this one here. I'll circle the whole thing because we mean the whole thing. This thing is called the Hastings correction. This accounts for the fact that our proposal distribution is asymmetric. That is, there's some different probability of proposing a move in one direction versus the other, so we're just accounting for that. And it's just exactly the ratio between the two. We're multiplying in the ratio of q of x given x prime divided by q of x prime given x. So this is our whole MCMC algorithm. So all we need to do in order to implement this algorithm is, one, we need to choose a proposal distribution. I'm going to talk in a bit about kind of the practical the practical notes in choosing a good proposal distribution. And then based on that proposal distribution, we need to derive this acceptance probability just by computing this ratio. And once we do that, we've implemented our MCMC. We run it just like with Gibbs sampling. We get a whole bunch of samples, and then once we run it and we feel like it's mixed, that is, we think that the samples are now a good representation of our true probability distribution, we can ask any question we want of the samples, such as, what is the probability that x5 equals 1, for example. Okay, I told you that Gibbs sampling, or that the Metropolis Hastings algorithm is a generalization of Gibbs sampling. So let me say now what I mean by that. We're going to see that, in fact, Gibbs sampling is a special case of the Metropolis Hastings algorithm. That is, it's the case when we use a specific proposal distribution. The proposal distribution we're going to use is the following one. We're going to find q of x prime given x equal to just the full conditional for xi. That is, we're going to pick one I and let that be the value we're going to change, and then we're going to hold everything else the same. So here we're going to have xi distributed according to this full conditional, and then this indicator term here, this is just saying that this proposal distribution assigns a probability of 0 to any proposal where x prime negative 1 or an x prime minus I doesn't equal x a non-prime minus I. So this is going to have value 1 only when these two are equal. So it's impossible to get any move where x minus I changes. It's only xi that gets to change. So that's all that indicator term is doing. It's just saying we're going to use this full conditional as our proposal distribution for xi. So now let's derive our acceptance probability. So it's this thing here that we showed on the previous slide. So let's plug in here. We're going to take the chain rule for this expression here. So we have probability of x prime. Well, this thing, according to the chain rule, equals this thing, probability of x I prime given x minus 1 prime, x minus I prime, times probability of x prime minus I. That's just the chain rule on xi prime. Same thing on the bottom. I'm just doing the same thing here, but for x instead of x prime. Now q, if we write that out, we get this expression here. I've dropped the indicator because we're only ever going to propose moves where this indicator is true. Otherwise, it's just going to be 0 on top and bottom. And so all that is this term here. Now notice that x minus I prime and x minus I are equal. So I've just replaced them here. So these cancel too, and those cancel. So this whole thing is just always 1. So that is to say that Gibbs sampling is this particular proposal distribution. And notice that in Gibbs sampling, we never rejected samples that like we sometimes do with Metropolis Hastings. Well, a reason for that is that we've chosen that proposal distribution such that our acceptance probability happens always to equal 1. So that is to say that Gibbs sampling, again, is just a special case of Metropolis Hastings where we're using this particular proposal distribution.